Welcome back, everybody. Now in this section, we're going to begin IPv6 addressing. This next lab or recording that I'm going to leave you with is just talking about the basics of IPv6 addressing, getting to know IPv6 addressing if you haven't done it in the past. So you'll be learning the format of the address, the types of addresses, the main two rules they need to look for, and just a little history lesson on where IPv6 came from, all right? And why is it that we need IPv6 and the tricks that they had to do to hold on to IPv4 as much as they could, because they were just, they just messed up and just said, here, 65,000 addresses. No, that's not the way it's done. All right, so this is an introduction to IPv6 addressing. This is the very beginning. Believe me, you're gonna have a lot more on IPv6 addressing and assigning to interfaces and routing and all that. It will be in this particular lecture. You'll get the whole shebang, okay? So I hope you enjoy it. You need to understand that, because definitely these are things that will show up in your certification exam. I leave you with the PowerPoints. Welcome, everybody, to IPv6 addressing. This is going to be very interesting. There's going to be a lot of lectures, not a lot of lectures, but several lectures on this particular topic. They take their time with it in the Cisco 200-301. They've changed things on me a little bit, but that's okay. So the first thing, as usual, we ask ourselves, why do we need IPv6? Well, for one reason, it's a larger address space, right? IPv4 only had 2.4 billion addresses. IPv6 has 340 undecillion addresses. And the reason for that is that we're using hex numbers instead of decimals, right? Because decimals, we made an upper limit of 255, right? Because if you put out the bit values from 1 to 128, right? 128, 64, 32, 16, 8421, that comes out to 255, so that's the maximum we could use. So when we do that for each octet, we come up with 2.4 billion, 2.4 something billion addresses. With hex numbers is very different. And instead of being a 32-bit address, like IPv4 this IPv6 is 128 bits. So it's a much larger address space. That is the most common thing that everybody says and they look at. It's like, hey man, this has more IP addresses so that we can use, okay? It was already ran out on IPv4. It was gone, all right? We have to switch to IPv6, but again, the transition is coming very slow, and you'll see in a second how slow. All right. Another reason, no broadcast. Everything now is multicast. There is zero broadcast. There's no ARP, nothing like that. It's all multicast. It uses neighbor discovery instead of ARP. Okay, so that's why there's no broadcast. Neighbor discovery protocol. Now we'll get into these, deeper. Not in this particular lecture, but in other lectures we will. We'll get deeper into the neighbor discovery protocol. All right, and there's obviously new features that come with IPv6 addressing, because it's not just saying, hey, we need a bigger address space, which we did, but all right, let's put some things in there that we can use, some special addresses, some special things that, that would allow us to make addressing easier. How about making the transition from IPv4 to IPv6 easier? So there's new features that are involved with IPv6 that gives you the reason, hey man, we do need IPv6. But the things that we need to understand is the hardware compatibility and application compatibility. There's certain, applications that will work perfectly with IPv6, but there's specific applications created for a company that was based on IPv4 that now has to be redone for IPv6, even though, as you'll see in a second, this is back in the 90s that they were trying to implement this. But you'll see. All right. And obviously we have a new header, okay, with IPv6. They made it more streamlined than IPv4. So they took out some of the fields that weren't really that necessary, or they crammed them into other fields, and they streamlined it. And it's a very fast protocol, right? Very fast routed protocol, so things can move a lot quicker. So IPv6 does have a lot of advantages over IPv4. One major advantage, and that's why it's taken so long to really embrace IPv6, is just the fact that the address is just so long, and since it's in hex, we get confused and we don't understand. And that's the major issue right there, because now we're not doing decimals. Because when you're converting decimal to binary, binary to decimal, that's very easy, right? But when you're doing from hex to binary to decimal, decimal to binary to hex, or just from binary to hex, that makes it a little bit more, not complicated, just a little bit more thought that goes into, making that conversion. Now, they have one of those new features, like I said, is transitioning into IPv6. That was the whole goal of it. And before we go into that second, but look at that third bullet. IPv6 was developed to deal with the death of the Death Star. No, the death of IPv4. All right. In 1998, IPv6 was drafted as a standard. 1998. Look when it became an actual internet standard was ratified in 2017. Hello, that's what? You see, from 2000 to 2017. So that's what, it's 19 years. And still, nobody is fully IPv6 yet. Okay, so it was transitioning into IPv6. What's the purpose? The whole purpose of it was to get rid of IPv4 and just use IPv6, because nobody expected, hey man, no, you've seen the movies, you've heard the rumors. Nobody needs a personal computer. Nobody's going to need that many IP addresses. Ha ha. Nobody wants to chat online. Nobody wants to see movies online. That is a fallacy. Well, yeah, no. That did not happen. That did not happen. All right. If you go on Netflix, there's a freaking movie. What's it called? It's a weird name. Heat and Catch or Health and Catch, some weird name like that. It's a computer movie, and it follows the evolution of the personal computer, and more specifically, Compaq. It has a different name. They have a different name called what's it called? The Big. Big IBM. I don't know what it's called. They gave it a name. Big PC. I don't know. But it's a good movie. It's a pretty good movie. It's a series, not a movie. It's a series. But it shows you how the evolution of the internet, people chatting online, people playing games online, all right? People using other people's network, right? All these different things that evolved from, with ARPA, and just the military using it, the government using it, to public citizens using the internet. Hell, 5-year-olds know how to use iPhones better than me. Okay? That's just the way it is. All right? So they never thought that was going to happen. And when it did, they said, oh my God, we got to come up with some tricks here. Oh, I know. Let's, instead of doing some class full routing, meaning everybody has the same subnet mask, let's do CIDR, classless interdomain routing. Right? Here it is right here. Classless interdomain routing. Right? We're gonna do that because we screwed up. We thought that we were going to. If somebody wanted 1,000 addresses, we can just give them 255.255.00. That's 65,536 addresses slash 2. That's 65,534. Oh, one of them was 1,000. All right. What am I going to do with the other 63,000? Grow your company. So they came up with CIDR. So now we can move the line to meet the needs of the network, right? They came up with NAT, right? It's the public addresses is the issue, right? Because we know now that there's private addressing, right? There's private IPv4 addressing and there's public IPv6 addresses. Well, with NAT, and there's 3 different types of NAT. You have static NAT, dynamic NAT, and NAT overload or PAT, which is the most popular because one, if you're using NAT overload or PAT, same thing, is using one public IPv6 or IPv4 address, all right, as to translate all these people that are private. They can do that. They can do that. That's awesome. That is awesome. All right. So they came up with these little tricks with IPv4. Oh man, let's do this. Okay. But eventually, that's going to go away because to support IPv6 routing, routers must understand IPv6 addressing and routing in order to replace IPv4, which is another case that we can make. There's still, certain routers that, not many, I don't think, because, as of Windows XP, the operating system, and I believe the iOS 4.3, we were already using, we were already IPv6 ready. All right, some routers, we're ready to go. It's just the implementation of every piece of hardware and every piece of software, okay, that is causing, still is, and fear. That's a major factor right there. Fear of the unknown. All right, getting to go to IPv6. Just take a look at it. 1998. Are you serious? And then it took almost 20 years, and they said, okay, we'll ratify it 20 years later. Wow. All right. So, but again, they played around with CIDR and NAT, but eventually NAT is going away. I mean, I'm not going to say even CIDR, but NAT is going away. Well, there is no subnet mask in IPv6. There is no, CIDR or nothing like that. That doesn't exist. It's prefix length. All right. So obviously you have IPv6 protocols. And you can look at the RFC. What's interestingly enough in this book, and honestly, even things that I've downloaded from Cisco, PDFs that I sent to people, they point you to an RFC. They don't give you a real definition. Okay. So IPv6 has more addresses. Okay. Go to this RFC and find out more. Oh, okay. So you go to the RFC and you get more confused than anything else. All right, but there are new IPv6 core protocols like RIP-NG, EIGRP v6, and OSPF 3. All right. RIP-NG, RIP is RIP, EIGRP is EIGRP, and OSPF is OSPF. The core set of routing protocols are the same. That hasn't changed. All right, the algorithms haven't changed. I'm sure they've updated certain things, but I'm no physicist, okay? But I'm sure the algorithm, some things have changed, had to have changed. But RIP is RIP. Now the configuration, which we'll be doing in later labs, we will be configuring these routing protocols. Okay. To be honest with you, it's a lot easier. It's a lot easier. Okay, it's a lot easier to do. Okay, again, they made it more streamlined for us, and a lot more features are available to us. Now, other protocols that were enhanced were ICMP v6. Extremely important because there's no ARP now. It's called neighbor discovery. It comes from that ICMP v6, neighbor discovery, right? Because just to give you a little sneak peek, because neighbor discovery means that now if a computer wants to find another computer or even a router, if the end device is the one that initiates it, well, it's a neighbor solicitation, right? Sends out that request. Hey, is anybody out there? And then if it's going towards a router, because the IP address, the router is going to send back a router advertisement, which is on multicast. Hey, yeah, that's me. Here you go. Here I am. Oh, okay, cool. So you have neighbor advertisements, neighbor solicitations, router advertisements, router solicitations. So you have all these things. And one very important thing that goes out with these things is DAD. You know, Dad's got to be around, right, to make sure everything's okay. That there's no duplicate address detection. That's why ICMPv6 is extremely important. Now, when I first heard that, I'm like, duplicate address detection? You have 340 undecillion addresses, and each subnet can handle 15 quintillion addresses. If you get a duplicate address, you can play the lotto and win. But obviously, I believe they're not talking about the interface ID portion of the address. They're more concerned about the network prefix of the address, specifically the subnet section, because it is very easy to overlap. If you are subnetting, it's very easy to overlap. So that's something new now, neighbor discovery, all right, and which is a good thing. And it's a good thing that we do have Dad there to check up on us. You know, dads, we're all paranoid. We got to make sure that, you know, nobody's playing around. So this duplicate address detection is there. And they have one more thing here. It's called the EUI-64. Now, we really don't care about the interface ID, which you can think of that as the host side of the address, right? The interface ID, right? Because it's 64 bits long, right? Could you imagine typing that out all the way? Man, it's a 120-bit address. I got to type all that. So you can use EUI-64, and just to give you again, just a brief overview of EUI-64 of what it does, it basically assigns an IP address for you, and the way that it does an interface ID for you, that portion of the address, and how it does that, it takes the MAC address of that particular interface and pads it, meaning it takes the MAC address, splits it in half, and puts right in the middle in a triple FE, right smack in the middle, to turn it into a 64-bit address. I'm not going to go any deeper than that because we will later on, but just so you know. So what do we have to worry about? All we have to worry about is the network prefix. That's where our focus is going to be on. So you can see, look at all these great things that they've come up, newer routing protocols, right? Same protocols, just different configurations. But a new ICMPv6, no more ARP, meaning no more ARP broadcast, no more broadcast at all. Everything is multicast, which is exciting. Now here's your breakdown, right? So here's an IPv6 address, like it says, the format. So as you can see here, let me get a little pencil here. I think it's already red. So this portion right here, as you see it down there in the table, I'm just going to underline it right here. And woo, that's not a line, that's a squiggly line. All right, so this right here is the network prefix, which you see down here. You see the 2001, here's 2001. Then you see the 3200 up there, there's 3200, that, and then you have the 1000. That's this right here. That is a network prefix. And each one of these is 16 bits long. You have 16, 16, 16, and 16. Well, that makes 64. Because 16 and 16 is 32, 16 and 16 is 32, 32 and 32 is 64. So this portion of the address right here is 64 bits. And this portion of the address right here is 64 bits. This 1, 2, 3, 4 sections. 1, 2, 3, 4 sections. That's why you see here 8 sections or fields or groups, whatever you want to call it, okay, of 4, 1, 2, 3, 4 hex digits separated by a colon, okay? So that's what gives you that 128-bit address. But again, this side of it, this first side right here, where the 2001 is, and ends in 1000, that is the network prefix of the address. The other side is considered the interface ID. Now I chose these numbers on purpose. This is your hex table. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, F. So that is your hex table right there that I used it to make up an address. And this guy right here, this guy is called your prefix length. You see what it says there? At the end is the prefix length. Yeah, this is what it meant by at the end. That's your prefix length right there. And that's why I said here, dissecting it. Basically, I'm just saying, whoa, sorry. Here, what I'm saying is, hey, okay, let's take the network prefix. So the first field, section, whatever group, okay? The 2001 is your registry, is the IANA. I always get confused. All right, there, the guys have the IP addresses, and they said, okay, well, this is a public address, and we're going to give you this public address, okay? Because when we look at the types of networks, the globally unique address is 2000, I think, :/3. All right, so we give you 2001, okay. So then the ISP says, well, they gave the ISP 2001, and then it gives them a 2000, then it gives them a 3200. So we have an ISP with a 2001 3200. Okay, so then the ISP gives the company, okay, the ISP is going to give the company bad. We can make fun. We can make face. We can make all sorts, dade, dad, whatever you want, beef. You can play around with it. It's up to you. But again, each ISP will have its specific one, and then the company, obviously. Okay, and then the one I have highlighted there in yellow, this is where your focus is going to be on, right here. This is what you need to pay attention to. And remember, each one of these digits, the 1000, this is not 1,000 people. This is 1000. These are hex digits. Each one of those digits is 4 bits long, making that 16 bits. Okay? So when we get into the subnetting portion of this section, you'll understand that. Okay? It's very important that you remember that we're not dealing with decimals anymore. These are hexadecimal numbers. So that's why, unless you're doing things statically, then you were, oh my God, I got to come up with an address. Okay, let me make one up. Okay, and you can make what? I mean, come on, you can make whatever combination of numbers you want in here. Okay, just be careful about overlapping. But that's what we got DAD. That's what we got DAD for, right? Duplicate address detection. And your router will scream at you if you do. But this is what an IPv6 address looks like. So you can imagine the first time I saw this, I was like, what in the world is this? All right. And what's funny is, let me see if I can get rid of this. Is there like an eraser on here? Yeah, there is. Erase. Let me erase this. That's pretty cool. All right. Oh, didn't erase it. Why didn't I erase it? There we go. Let's get back the pointer. All right. The laser pointer. So, this guy right here, okay, the 64, they say to use that if you don't know what the hell you're doing in IPv6. That will be the default, right? That will be cutting this in between right here. All right, you can't come up with any subnets. It is what it is. The 64, you're in the 1000 subnet. That's it. Or the 1000 subnet. Now, then you can put it, look, we have subnetting 200, 3000, 4000, 5000, all using the 64. Okay? That's pretty easy to subnet, right? That's not bad at all. All right? Make it simple on ourselves. All right, so you can do that. So this 64 is like a default, okay? Not that it does it by default. You will have to put it in there. But if you don't know what to put, just put a 64, okay? Just put a 64. When you start doing the labs, you'll understand what I'm talking about. You understand? All right, so one of the big things is the header. So I get the testing purposes. I guess for your knowledge at work, so you can sound smart. I mean, I don't know. All right, things they kept, right, from IPv4.basic. So they kept the version field. So we have the same version. Well, not really. This is IPv4. This is IPv6. Okay, and then we kept the source addresses much bigger on this side. Destination addresses much bigger on this side. No, okay. And what is this here? Fields that we didn't keep. Oh, we didn't keep any IHL, identification, flags, frag when out checksum, all this stuff. Yeah, we don't need all that. We just don't need it. Okay. So, but we kept the traffic class. So we some fields actually, they put it they crammed it into a particular another field. You know what I'm saying? And they called it differently. Traffic. You don't see any traffic class here, do you? So here you have type of service. So traffic class. Okay. We don't have no flow label over here, right? That's new. That's new. It says it right there. That's new to IPv6. That's new. It's a flow label. Okay. Then we have a payload length. Well, here they had a total length. So now we had it called a payload length. Okay. So we added certain things in there that we didn't have before. Because you hear next header, that's we don't have a next header. We didn't have that there. Okay, so we have it here. There is no broadcast, right? No ARP or anything. We need to know the header. Okay, and then a hop limit. It's like a TTL, I guess you can think of it as that way. So these things were kept, but you can see that it's a lot smaller. It's a bigger address, hence the size. Okay, but it's a lot more streamlined. There's not all this other padding and options and all this overhead that they had in IPv4. IPv6, they made it more streamlined. They make it look bigger because it is bigger, okay? But again, you don't have all this other stuff that you really didn't need, okay? You didn't need, or it's built in. Now, this is where things get really interesting and in their terminology. And these are the PDFs that I downloaded from Cisco that I sent to people. And, it's like, I'm reading it, as I'm doing this, and I'm like, what? And that's why you see what there. So here we have this guy right here, the colon 128. The name of it is called unspecified. What is it? Well, it's a source address. It can only be a source address, and it's used by a host that just turned on. I love this word, initializing. Makes you sound smart. A host that just started, right? Before it knows its own address. So before it knows its own address, it has this. Oh, okay. All zeros. Okay. And then this one really threw me for a loop. Loop back, right? There's only one loopback address. That's it. Period. It's only one loopback. This is their description. Host talking to itself. When I read that, I was like, what? Because in IPv4, because when they make the comparison, they compare that to the 127.00.1. The definition for that one, it's checking the TCP-IP services. So on IPv6, it's just talking to itself. That's their definition. It's talking to itself. I hope that's not a multiple choice answer. I'm pretty definite you're still checking your TCP/IP. Okay, version 6, but TCP/IP. You're still checking that. But just so you know, that's why you see I put what? I listened. I looked up everything I could look up, and it's talking to itself. Okay. So when you ping your loopback, that you get a reply, you're still checking your TCP/IP stack, okay? But just know that they call it talking to themselves. All right. Then the next one we got FC00:7. And the 7 still represents, though, how many bits, okay? 128 bits, because it's an 128-bit address. 7 is the first 7 bits of that address, okay? Those are unique local addresses, all right? Meaning private addresses, all right? So probably like 192.168 or 172.16 or the 10, you know what I mean? So these are private IPv6 addresses, all right? So obviously they're for internal use only, all right? Now you also have FE80. Now what's interesting about that, see, is a CIDR 10. And I put the binary there, as you can see, because F, this is F, this is E, and this is 8, and then 0, 80, because the CIDR is 10. So this would be the binary of this FE80. So that has to match that in order to be that. So basically it's the equivalent of the APIPA. And it exists on every interface on there. You can create your own FE80 if you wanted to. I don't know why, but okay, but you may want to for some odd reason. Okay, create your own FE80. All right, you can go ahead and do that. Link local address. All right, you can do that. Don't take it out. Okay, it's there in case I guess backup purposes. All right, you can go ahead and you can, because you can only have FE80 addresses on your same segment. It's like the APIPA. They're not routable addresses. You can't route with them. They have to be within their own segment. They don't leave. Okay? So same thing goes for this like local. Okay? Now in the book, I know in the ICMD2 book they have it. It's like you can use the FE9, the FE8, the FE9, the FE10. I think they say A. I'm sorry, FEA. FE. No, you can't. Because the RFC states specifically FE80. That's what we will use. FE80. There is no other link local address, period. All right. Now somebody was concerned about Torito, and apparently this is the address or the network prefix. The network prefix, which can be used in IPv6 for NAT to map to the IPv4 address, and then you can go ahead and use NAT with this Torito method. All right, or you can use 64 tunneling if you're going across the network. Again, it's a mixture of IPv6 and IPv4. Really what it's doing is encapsulating IPv6 into an IPv4 address or vice versa in order to be able to get across a wide area network. These guys are global unicast. What is that? Public addresses. Eventually everything will be public. Think about this. I mean, seriously. You saw the format of the IPv6 address. If one subnet can give you 15 quintillion addresses, hello. Do you really need anything else? No, not really. Okay? So think about that. Think about that. All right? And then we have this. FF00:8. Multicast, same purpose that we use IPv4, but now they're in hex numbers. So anything you see with an FF is a multicast address. And these addresses right here, this is simply memorization. All right, in case they ask you, you know what they are. Don't say what, okay, or a host talking to itself, even though it's in their literature. All right, but don't know. Okay, don't do that. All right, testing TCP-IP stack. You know, it's a host that assigns itself that IP address before it actually gets an IP address. It's unspecified. I don't have an IP address. All right, so there. Because FE80 will always exist. So it's not like before you didn't get an IPv4 address, therefore you had your PIPA, but in this case in IPv6, you always will have an FE80 whether you have an IP address or not. Okay? So that's why they call this unspecified. So this is just basically just memorization to see if which one they pop out on the test. It's like playing Jack in the Box. You don't know what you're going to get Jack in the Box. Okay? And then you have the Anycast. This is interesting. This is Anycast is supported explicitly in IPv6 RFC. What I messed up my number there. 4.2, I think it was 4.2.1 in there. But you can just Google it, look up the RFC for IPv6, and go ahead and read it. I dare you. Okay. There used to be a network prefix. It said it came from the FC, from the unique local addresses. Not anymore. Now it's NA. Now anybody, right? Just any type of address you can use, and then as long as you put you should operative word should use 128 like a host address, like when we do the loopbacks in IPv4, we put a 32-bit address 255.205.205.205. Here's 128. Okay, we put a mask of all 255s, 32 bits. Here we will use 128 bits. And you should use that. So we will look for that specific address when you're looking at a service. Okay? And then you have to type Anycast to make it Anycast. Because now it'll just be an address. A regular old IPv6 address, you got to put Anycast behind that. But you should use 128. You should use 128-bit, all right, for the prefix length. And basically, I mean, the way that, some routers is hosting some sort of service that you need, because this Anycast address can exist. And again, there's not one specific Anycast address. All right, it could be any, but you choose, okay, let's use this address from this range, whatever. And at the end, when we're configuring, we will type Anycast That will be the anycast address. Then you put that same address on all the routers. All right, because one other advantage of IPv6 is you can put multiple IPv6 addresses on the interface. You can do that. You can do that. Yes, you can. Okay, so if you're using that, this is also called the one to nearest because it's looking for a particular service. So it's going to be looking for that address. But how does it know? Because it's one to nearest. Which service is nearest me is based on the routing protocol, how you're routing. Okay, so keep that in mind. Keep that in mind. One last thing to round this off is rules. There's not that many rules. We only have 2 rules there. Leading zeros can be removed and no double colons in the address. And there's your example. Look how long that address is. 2001 3200 bad 1000 00 0003 0012 0 A B C D 0001. If I had to type that out, that would be obviously everybody's copy pasting. All right, but they did something awesome. They said, "Hey man, you can take out the leading zeros. Just take it out." Right, and that's called shortened expression. It's still not short to me. I can tell you that right now. But short expression, you can get rid of those leading zeros, and it can be on either side. It can be on the interface ID. It can be here, no more than here because this is your ISP. But it can be up to here. You can take out the leading zeros. It still be valid. That'll be a valid address. Okay, take out leading zeros. Just think of your paycheck. Think of your paycheck. Do you want zeros in front or zeros in the back? All right, you want zeros in the back, right? You don't want any zeros in the front. You take out those zeros, or else you ain't getting paid squat. You want like 8 zeros in the back. Yeah, that'll be nice. All right. So leading zeros, you can take them out. It will be valid. All right. You can see the example. They're highlighted in red. Okay. They're colored in red. So you can see those are the ones that I took out here. 3, 3, 12, 12, A, B, C, D, and then just. Well, look, I didn't take out that 0 here. I could have taken that out. I forgot. Okay, so the other one is the double colon rule. You cannot have 2 double colons. And here's the example. So here we got an address. I'm trying to make it simple. All right, you got a set of all contiguous zeros here. Then you got zeros here, and 12 contiguous zeros. Then 0, 0, 0, 0, 1, right? So here, look, I did it again. Okay, whatever. That's what happens when you copy paste. Here, we decided, hey, let's take out all the zeros. We truncated it, so that's a double colon. And then we truncated this one. We took out these zeros. We forgot to take out all these zeros. All right, whatever. All right, so, but you have 2 double colons. That is invalid. That is invalid. You cannot have, I don't care if it's here or it's here, you cannot have 2 double colons in the address. Only one. Only one. Because then if you don't, if you have this right here, what's going to happen is that the IPv6 routing protocol, IPv6 protocol is going to be like, huh? I can't make a decision. Where do I put the 0? I don't know. So we got to tell it. So that's why we come down here and say, look, we can put a 0 here, or we can put a 0 here and here. We don't want them to get confused. As long as you put 1 0 on one of these, you're fine. It's valid. Okay, you want to put it on both? That's fine. It's valid. All right, but that's it. Those are the main rules as far as that you need to follow, and more than likely, at least for the CCNA 200-125, they really, 90% of the test was just validating addresses. For this new test, we shall see. We shall see what they will ask. But this is an introduction to IPv6 and the features and the types, and obviously the large number of addresses that exist in IPv6, which, by the way, 340 on the ceiling. I looked up for different analogies. One analogy that I like that they used, I don't remember where I found it, somewhere online. They said that a grain of sand. So you take a grain of sand and fill up a dump truck. That would be IPv4. And then you take that same grain of sand and you fill up the sun. That would be IPv6. So, and nowhere in my generation, the next generation, the next generation. I mean, we literally can hold hands across the world if we have that many people in the world. 340 undecillion. That would be insane. Or that many devices that need IPv6 addresses. That's crazy. There's no such, no, unless we're now talking about, now it's not only we're networking globally. No, we're networking now the galaxy. Oh, okay. That's a different story. Now, now we're doing networks to connect to the moon, to Mars, to Jupiter, to even Pluto, though it's not called, what is it called? There's something in front of a minor planet or small planet, something like that. I don't know. Whatever. Okay, you know what I'm talking about. So now, if we're networking the galaxy, well, that's a different story. But if we're networking just planet Earth, 340 undecillion addresses, I think that's good. I think we're good. Okay, because we only have 7.17 billion people. Yeah, we're nowhere near 340 undecillion addresses. So that's an introduction to IPv6. I will see everybody in the next lecture.